of the FinFET. Now, let me talk about quantum confinement again. I did not discuss this well last time, but doesn't matter, right? It's just an equation, right? But let me still just say a little bit more about this quantum confinement effect. First of all, this is an infinite quantum well, right? If you have learned about quantum mechanics, you know that the minimum energy here is not zero, is E1. I should call it E0 and then E1, right? When you have a quantum confinement effect, a particle inside this well cannot attain the lowest ground state energy, which is zero. Then for you, as a particle, what do you think? You will just feel that it is as if the ground level is at E0, correct? Because I can never go to any energy lower than E0. Then for me, for practical purpose, the ground energy is E0, right? And if we solve the Schrödinger equation, you find that you can only take discrete levels. Right? So this n go from 1 to infinity. Because of this, then I need to change this back to n actually, right? So in the first level, the energy, this one is what? H bar squared divided by 2m pi squared divided by LC squared, right? Because n equal to 1. Then later to another level, it is going to be 2 pi squared, right? So increase by 1, 4, 9 in terms of the energy, right? And then what? 16 quadratically. That is the so-called quantum confinement effect. But why I want to talk about this? That is because in FinFET, we have a lot of quantum confinement effect. FinFET is very narrow. It is just a fin, right? If you try to look it as a double gate, it will be something like this. Let's say I have a FinFET like this. I have 2 gates, correct? Now my question to you is, as an electron in the conduction band, this is an electron, but it's actually against just a quantum mechanical particle, right? Can it get the energy of EC based on this? Classically, we say that I put the electron in the conduction band. Its energy is EC. Now I make it so narrow. What will be the energy of this electron? Anyone? What is the energy with electron? I don't mean to give me the number or equation. Just tell me what happened to the energy of the electron. If it is classical, it's just sitting on the conduction band. Now I make it very narrow. What happened?
It remains the same.
It remains the same. How about let's look at this one more time. I have a well. If it is classical, the particle will sit at 0, right? You do have something called E1 because you always have one energy. But because of the quantum mechanics, you don't attain the lowest energy. You are actually here, right? its energy increase by h bar square over 2 pi, pi square over 2m, pi square over LZ square. Are you okay? Everyone okay with this picture here? If it's classical, right? You have a jar, you have a well, you put a ball inside, the ball will just stay at the bottom level. But quantum mechanically, it tells us that when you make the well very small, actually it doesn't have to be very small. But anyway, let's say make it small, then your particle cannot touch the ground of the fall. Its energy is going to be here.
What does that arc represent above it?
Say again.
What does the arc represent above the?
Oh, this one. Okay. This is the so-called wave function. So it is no longer a particle. It is the electron becomes a wave. And this one show is the probability amplitude of finding the electron at that particular location. That is so-called wave function. So you can have an electron here, and this is the wave function of the electron. If your electron has higher energy, this is the wave function of the electron at that level. Remember tunneling? Why there is a tunneling? Tunneling is because electron is a wave. So yeah, for a classical electron, when I come in, I will just bounce back, right? But because I'm a wave, well, I will attenuate. I have a finite probability, however small. It's very small, but I still have finite probability to go through. If I'm a particle, I keep running into the wall. Theoretically, maybe I don't know, maybe in 10 to the power 100 seconds, I will go through the wall without problem for the mass that I have. This is a quantum mechanical effect, but I'm a bulky subject, so actually you don't see a lot of quantum effect. But electron is a very small object, so you can see much more of the quantum effect, right? So this is more like quantum mechanics. You can describe a particle as a particle or a wave. In Schrödinger equation, you basically is treating everything as a wave. And if you solve it, this one tell you the probability of finding the electron at a particular location. Or let's don't go too deep, just say this is the wave of the electron. Or if you want to say classically, you say, oh, this particle just sits at this level, it cannot go down. Do I answer your question?
So yeah, so the arc there you'll find it in that particular area.
Sorry, there was noise. Can you say again?
So that arc represents the chance you'll find the particle in that particular area?
Yes. For example, here you have very small probability to find the electron. Here you have the largest probability.
Okay, thank you.
And if you integrate the area, you will get 1. It's not exactly area, but related to area. It actually is at the square of the wave function, give you the probability. But just treat it as that way, okay? Okay, now, can I go back to here? Someone tell me, classically, the electrons sit on conduction band. What happens if there's quantum confinement effect like this? What happened?
Higher energy?
They have higher energy. Can you explain whatever? I don't know. Just say something. Why?
Because the example, when it's confined, I guess it cannot be the lowest energy.
Yeah. When it is confined, you cannot have the lowest energy. Lowest energy is easy. But now, no. I will just stay at this level. This is easy. plus h bar squared divided by 2m pi over Lz squared. Let's say this is Lz. Your particle is here. And if you want to draw the wave function, it is here. Of course, they are not exactly the same. This is an infinite potential well, then you can use this equation. This is finite triangular well. You cannot, but this is the idea. Okay? Well, that is applicable to the hole also. What if I have a hole here? After quantum confinement, where will the hole be? It's going to shift also. Correct? So the lowest energy electron and the lowest energy hole, they are separated further. This was the band gap. And now, this is the band gap. So what do you see? Increased quantum confinement. Increase the band gap. Well, I did not change the silicon. Silicon is still silicon. But I changed the band gap from 1.1 eV to 1.2 eV. Right? It's just like I have a new material. Is that a big deal? It's a big deal. Think about that. In the past, if I shine a light into here, if the light have the energy of Eg, it's going to generate electron hole pair. Now, if the light reach here, because of quantum confinement, it cannot generate an electron hole pair unless the energy is larger than Eg dash. Right? If you're only Eg, you try to place in conduction band and valence band, you say, oh no, quantum confinement. You say that I cannot occupy this level. The nature doesn't allow you to do that. So originally, the light got absorbed, so it is opaque. And now the light will go through, it becomes transparent. This is a big deal in the photonics, in the laser industry. They said they are very important, this quantum confinement, okay? Any questions? If not, then I want to move to density of state. We learn about density, I think, I don't know if you learn about that, right? But I will review because it's important. Don't think it did too much, density of states. It's not too difficult. It's just like the name said, the density of state. It's a quantum system. Quantum system is very interesting. Everything has to be in order. If I don't give you a ticket for the seat, you cannot come into the room. You cannot say, I stand there. I stand between the seat. There are some states, just like the seat. You need to get into one of the seats. Otherwise, you are not allowed to come in. Forbidden. Okay? So densities of state is basically telling us, for example, I give you a fake example. This is the energy. And let's say this is 0 eV. Okay? And then this is 1 eV. This is 2 eV. This is 3 eV. It's not difficult to understand. Just think about 1 eV is the first 4. Second eV is the second 4. 3 eV is the third 4. And then 1, 2, 3, 4, 5. Between the ground and the first 4, I have 5 stairs, okay? Or let's say 5 stairs, right? They allow you to sit in the room, just the stairs, right? So can you tell me how many states are here? Between first 4 and the second 4. That's between the ground and the first 4. How many states are there? I have 5 stairs. How many states are there? Let's say each stair allow you to stand. and watch the lecture? How many?
5.
5. Right? Don't you see? It's so simple. If hey, you're teaching me something like kindergarten. Yes, 5. Now, what is the density of state in this region? Between 1 and 0, what is the density of state? 5 divided by 1 EV. So it is 5 per EV. That's it. It's just now you're telling people, density of the stair is 5 between the ground floor and the first floor. Let's say I cannot find any stairs between the first and the second floor. How many stairs do I have? Right? I did not draw anything. I say I don't have any stairs. How many stairs do I have?
So 1.
0.
I say no. Yeah. So no, this is not a very good one-to-one comparison, right? So just take my verbally. I say no stairs, right? You may think then, how do I get up? You right? You think this is a trick or something? No, right? Just no states, right? How many? What's the density of state in this region? What's the density of state?
0.
0. I have 0 state per 1 EV, so it's 0. Let's say here between the second and the third floor, I have 2 states. Okay, so how many states? I mean, I have 2 stairs. I told you already, 2 states, right? So this will be 2 per EV. Is that okay? This is just a fake example. Indeed, if you try to look at any rigorous solid state physics book, the title of density of state, they really say counting of states or states counting. Indeed, we are counting, but however, we need to use integration to integrate the volume, integrate the number of states, but it is really just a matter of counting, like the kindergartner. Okay, but in reality, of course, we don't separate that far, right? We usually will say dN, dE. So for a very tiny energy level, how many states do we have? That's the question we try to ask. And that is so-called density of state. Any questions? Is that clear? Right? So you need to do differentiation if you are given, right? For example, if I say, yeah, this is fake example. Let's say n equal to E square, then dN dE equals to 2E. So your density state is 2E, right? It means if you have a higher energy, you have higher density of state. Okay. Now, the interesting thing is this. If you have a 3D material, what does it mean? It means it is 3D. You can go to X, Y, Z direction. The density of state goes up with square root of E. So when your energy is higher, we do see more density of state, right? It's just that you go to higher floor, somehow that the stairs becomes denser, more stairs between each floor. But it does not go up as fast as before. It's square root. Okay. Now, if we go to a 2D system, that what we call the quantum well, this one maybe you cannot see why it is 2D. Let's look at the 3D picture. This is the Z direction. Why it is 2D? Because the electron can move in this direction, they can go up and down. but they get confined in this direction, just like FinFET or SOI, right? You can go up and down, but you cannot go left and right. So that's why it's 2D, 2-dimension. Just imagine you are a little creature. You walk on the table. You can never leave the table at the end. Then for your purpose, this world is a 2D world. You cannot imagine what is up and down. And in this system, the density of state becomes a constant, right? And this just because this is a different level, so I don't want to go to this, but it becomes a constant, right? So, but here the main point is to tell you what is a 2D and what is a 3D system, right? Maybe the best, let's go to this slides. These slides give you a better view of what is 2D and 3D. 3D means I have 3 degrees of freedom, just like we the human being, right? But actually, before we can climb the tree or before we invented the helicopter, before we can climb the mountain, we are actually 2D creatures on the surface of the wall of the earth, right? But anyway, what I'm trying to say, the density of state go up as square root of E. When it becomes 2D, you see here, I cannot go left and right? Do not argue with me saying that, hey, look at this, I have a finite width, I can still walk for 2 steps left and 2 steps right. That is not the main thing, because now it is so thin that you are confined, quantum mechanical confined, you are wave function. You actually cannot transport to left and right. You can only have a wave going up and down, right? You cannot generate a wave left and right. Then the density of state becomes constant. Well, what if it's 1D? Can someone tell me an example of 1D? When can we have 1D? What type, or how about 2D? What type of device is 2D?
Like a sheet?
Say again?
Sheet, nano sheet?
Nanosheet. Nanosheet, or let's just maybe 3D is just everything, right? Bulk resistor. This is bulk resistor, right? 2D, you can say nanosheet, right? FinFET, sometimes fully depleted SOI, right? If you cannot see it, just draw it. For example, FinFET is so thin. The electron, right? Yeah, again, we don't think it's a particle. You cannot go these 2 directions, but you can go up. You can go into this direction from source and drain, right? So the density of state is like this, constant, when the energy change. How about 1D? Anyone know about 1D example?
A wire? Is it?
Yeah, someone say nanosheet, right? You say nanosheet, so nanowire. Have you heard about CNT? Carbon nanotube. Oh, this one is interesting. You see, it has a singularity when the energy is 0. Infinity. Well, this is very important for optical application. A very large density of state means they have very good absorption rates, because absorption means that even you generate the electron hole pair, you need to put the electron hole pair there. If you don't have density of state, it means you cannot put there, right? It's just like I try to kick someone to the first floor. If the first floor is blocked, right, no space, no matter how I kick, I cannot excite the person to the first floor, right? But now it has infinite number of room. Wow, it just keeps absorbing all the energy, right? And the last one, 0D. Do you know what we call it? 0D just say you cannot move anywhere. You just confined in all directions. You're stuck there in a cell. Any example? Do you know what we call it? Maybe I think you heard about that. You cannot associate quantum dot. It just have a delta function here. Here, the density state is even larger, right? It's an infinity within a very small region, right? So quantum dot, I think you see people talk about quantum dot LED, the organic, all this organic LED display, very expensive TV. Right? They have a very, I forgot the detail. Anyway, they are good, right? So I actually really love device physics. If you're doing well, you associate to everything in your life nowadays. LED, right? Quantum dot is everywhere, right? So so why do I want to introduce this? I actually almost not that useful for you now in this class, except that you need to understand we are doing doing the 2D and 1D system for our nanowire, for our FinFET, and later for gallium nitride, we're using HAMT, which is also a 2D electron gas. I will explain later, but not now. Any questions? Okay, good. So we know the density of state, right? So here is just the equation. I just repeat again. And you see this is the equation. 3D is square root, right? And then 2D is constant. 1D is 1 over square root. So you know that there is a singularity there. Well, you have room, but you need to tell the nature also how you are going to occupy the room. The nature has two distributions for us. The first thing is you're pretty familiar, called Fermi-Dirac Distribution. We have been playing this we keep playing this, right? When we talk about transport, we talk about PN junction, we talk about band-to-band diagram, band-to-band tunneling. Remember, I always draw something like this, and I talked about this already. Fermi-Dirac, I think this is the 10th time. I hope that now you're very familiar with this. This tells us the occupation probability, not this one. This is the energy, and this is the occupation probability. Can someone remind me how does it look like? Can you tell me how should I draw the Fermi-Dirac distribution in this diagram? Oh, someone drew it? Great. Who did that? Okay, Alex. But how do I erase yours? Okay, very good. This is, let's call it Alex curve. Okay, yeah, very good. He drew something like this, but I want to be more precise. So Alex, since you did that, right? Tell me, I see that you show me that when energy is high, then I have a very low distribution, right? And then you also show me that when the energy is low, I have a high probability, right? Although your shape is not exactly the same, but I think this is just the mouse problem. But I still want to take two quantity. What is the value here? And what is the value here?
0.5.
Say again, the first one is what?
The middle is 0.5 and the other one is 1.
This is 1. Okay. So this is 1. Very good. Because we're very low energy, they will all get occupied. So we have a story of building with 100 levels, right? Naturally, you can, yeah, it makes sense, right? Everyone is lazy, no escalator. They will occupy the first floor first and then second floor. You come late, then you go to the third floor. So at low energy, they will get occupied. Now, my question was not accurate. You are right, this is 0.5, what I'm trying to fish for, right? But this is only true. So let me don't do this because you will get confused in the future, I will going to move this one to here. Right, so this is 1. This is only true if this is the Fermi level. Okay, so at Fermi level, it is 0.5. So this is the equation. Again, we discussed this before. Exponential E minus EF divided by KT plus 1. This is the Fermi-Dirac distribution, right? But actually, I should do one more thing because I want to compare with the Bose-Einstein. I call this mu. Mu is the so-called chemical potential. If you remember all the chemistry you learned before about the standard cell, not the, I forgot what the battery, right? I forgot what you call it. The battery, right? Sulfuric acid with lead, they do reaction. The two cathode, anode, they have so-called chemical potential, right? In this particular case, chemical potential is also called the Fermi level. Is that okay? Now, not all particles do this. What particle will obey the Fermi-Dirac distribution? Right? You can think of this, right? Two types of people. You go to the building, only the adult will go to the higher level if the lower is occupied. If they are all baby or kids, they don't care. They will just go into the same room even it is occupied, right? They don't care if any people is there, right? So for adult, they see that first floor is occupied. Oh, sorry, I don't want to disturb you. I go to the second floor. This type of particle are not called adult, they're called fermion. Fermion. And they obey Fermi-Dirac distribution. I should not say that. They obey Pauli exclusion principle. So what type of particle obey Pauli exclusion principle? Can you give me some example? Pauli exclusion principle is just like the adult. If this room is occupied, I'm not going to go into the room because I'm trained not to do that, right? What particle obey Pauli exclusion principle?
Electron?
Electron, right? And many more. Proton, neutron, right? And they all have so-called how do we call it? Long integral spin. For example, electron is half, some particle are 3/2, some are 5/2, etc. Okay, so this particle, they never occupy the same place. They're well educated. I should not go to other people's room, it is occupied. That is Fermi-Dirac distribution. Another thing is called Bose-Einstein Distribution. This is very interesting also. Although we don't have much time, I'd like to tell the story, right? Bose is a scientist in India at that time, right? But he was not famous. And he discovered this. He had to write a letter to Einstein to say that, hey, can you check if I'm correct? And then, of course, I guess Einstein has some contribution. They call it Bose-Einstein Distribution, right? So it's a little bit unfair in some sense, right? So the distribution is different from Fermi-Dirac. Almost the same. E minus mu divided by KT, but minus 1. Okay, and we are not going to draw the graph. There's nothing to draw. The most important is that, what do we call it? We call it boson. They are the kids. What if the room is open? They just go in. They don't care if anyone is there. Just go in to play, right? They don't obey Pauli exclusion principle, right? Right? They can occupy same state. They don't have this exclusion. Okay, and they all have integral speed. What does it mean? 0, 1, 2, 3. Do you know what? Do you give me some example? What a boson? Do you know?
Photons.
Photons. What else? That related to device physics. You don't know.
Photon.
Photons, yes. Photons are quasi-particle, right? But they obey Bose-Einstein distribution. So what does it mean? You all heard about laser, right? If someday someone come to you say that, invest me for $1 million, I'm creating an electron laser. That will be the best weapon in the world. The first thing is that you don't kick him or her out immediately because he might be meaning other thing. It might be something variable, but you need to be very suspicious. Laser is talking about all the particles occupying the same state. And that's why they're so powerful. They're exactly in the same phase. So all the photons, they go in the same direction, have the same phase, same wavelength. And that's why they're so focused, so powerful. They can do that because they are boson. They have the same state. Electron is fermion. So if someone say they can make an electron laser, you need to be very careful because electron cannot occupy the same state. The best is that you have opposite spin. You only have 2 electrons having this state, right? But maybe they come up with some extra variable allow you to have the same state. We don't know. But that is why we never heard of electron laser. We heard of electron gun, right? Even the military, they say want to have some electron gun or whatever to shoot the plane. But mostly it's laser. Okay, my internet connection was not that stable, but I won't repeat because it's not very important, right? So basically you have Fermi-Dirac distribution and Bose-Einstein distribution. Both of them will converge to something called Boltzmann distribution. What does it mean? It means when E is much larger than mu, or basically just that if you have a high energy particle, just look at the Fermi-Dirac, when E is very large, then this is almost equal to 1 over exponential E minus mu kt, right? Because E is very large, and exponential of E minus mu is much larger than 1. And this is just equal to exponential negative E minus mu kt. And you know this in your chemistry, right? In the gas molecule. When they become very high energy, it's just Boltzmann distribution. And whoa, it's just telling this part. This is just the so-called Boltzmann distribution. Okay, something like this, right? Now, so it's very interesting in the solid state physics, they do have something like this, right? They talk about helium. Helium, I forgot which one is which. They have helium-3, helium-4. They just have 1 extra neutron. Because of 1 extra neutron, helium-4 is Bose-Einstein. I might say the wrong thing, but assume that I'm right. Helium-4 is integral spin, right? Because I have extra neutron. So at room temperature, just an ideal gas. But when you cool it down, it becomes Bose-Einstein condensate. They all occupy the same bottom ground level. But it's helium-3, then they are not the same. They will give you Fermi-Dirac distribution, right? So this is related to supercooling and yeah, something like that. Okay. Now, why we talk about Bose-Einstein? Because at the end, I will need to talk about a little bit about superconductor electronics. Superconductor is what? So-called Cooper pair. It's a pair of electrons. A pair of electrons instead of integral, half integral, it becomes integral spin. Then it means you can have all the electron Cooper pair in the same state. It gives you a macroscopic quantum stuff, quantum system, right? It's so large in micron order, but it's exhibiting all these quantum phenomena, and they can use for superconductor computation or whatever. Okay, so I taught a lot, but the basic message is that we have Fermi-Dirac distribution, we have Bose-Einstein, right? I hope that you understand there are two types of particles in this world, and in the extreme case, they become Boltzmann distribution. Is that okay? Right? And here I show the Fermi-Dirac distribution. We flip the scale, right? This is the energy, and this is the probability, right? So here, this is 1. And the most important is the temperature effect, right? When you have a higher temperature, you actually excite more high energy electron. But no matter what, at Fermi level, the probability is 0.5. I hope you memorize this at Fermi level. Okay. Okay, now we learn about states, we learn about distribution. How do we calculate the number of electrons that we have, right? Probably in the previous class, we learned all the equation, but I think many of us, including myself, when I first taken those classes, I don't know what exactly it is. For a class, we want to learn intuition, right? Not the math. Math, leave it to the computer, or leave to the, if you're a manager, leave it to your engineer, right? But we want to learn how to calculate. So first of all, it's just like the building example. I need to know how many rooms are there, correct? If I want to know how many people in the building. So let's start doing this. Looks like very naive stuff. Counting. Okay, I need to take my cheat sheet to make sure I have the right number. Right. This is just the example. I'm giving you the energy scale, right? And then I tell you how many states it has at different level. Here I have 2 states. At 1 eV, I have 4 states. At 1.5 eV, I have 1 state. At 2.5 eV, I have 1 state. At 3.5 eV, I have 2 states. Is this okay? Does it make sense to you? I just say that, well, in my system, I have different energy level. At different energy level, I have different number of states. I basically saying that you cannot occupy this part because I don't have state for you. It's just like the band gap. Any questions? Now, I also assume my Fermi level is here, right? It's important to get the Fermi level. I assume the Fermi level here. Okay. So I have the number of states, but I don't know how many people are in the room. Then what should I do? Well, I know my people are adult. They are fermion. They obey Fermi-Dirac distribution. So I know that they have this probability of occupying the room, right? And let's say this is 0.1, right? This is 0.3. Of course, this is 0.5, but we don't have any room there. That is okay. Let's say this is 0.9. At 1 eV, it is 1, right? And here it is 1. Does this make sense to you? What I'm drawing? I hope that you can follow it. Just tell me if you don't understand, because if you understand this, the rest is just equation. Forget about it. I'm not going to ask you to memorize the equation. Does that make sense? Right? So this is the distribution. right? Why do I choose Fermi-Dirac? Because we're talking about electron. They are adult. They obey Pauli exclusion principle. If it turns out it's photon, they are the kids. They just try to go to the lowest level. They don't want to climb up. Then once you get this, what do? Find the number of electron at each energy, right? So maybe I should do this. Let me use another color. Can you tell me how many electrons are there at this level? I have 2 rooms and the occupation probability is 1. Well, how many? Say again.
2 electrons.
2. Right? I have 2 rooms. Each room is occupied. How about how many electrons do I have here?
4 electrons.
4. Very good. How about here? How many electrons do I have?
You have 90% chance.
Thank you. Right. So this is just a fake example. Of course, we don't have 0.9 electron, but just an exercise, right? In reality, you have many more states. How about here? How many? How many electrons I have at 2.5 eV?
0.3 then.
0.3.
0.3. Thank you. Please do try to answer if you can. This one, 0.1, right? Okay, finally, what is the N? Means the total number of electrons in my system. Well, addition, right? 2 plus 4 plus 0.9 plus 0.3 plus 0.1. That gives me 7.4. So that's how I find out how many electrons I have in my semiconductor, right? A toy model. But I hope you understand every step. Because you understand this, it means you can do even the programming. Write your own device simulator.
Professor,
So yeah, go ahead. What?
sorry. Can you just tell us, where did we get the number of states from?
It is given.
Okay.
Yeah. So how do I get it? In reality, here. This is how you get the number of states. How do you get this equation? You actually need to go to solid state device physics to count the state. This is too much, right? But if you have learned the solid state device, you understand that you have some boundary condition. It will force you to have only certain possible value, and this is also related to confinement. For example, for this infinite well, I can count the state already. I know that at E equals 1, I have 1 state here. E equals 2, I have 1 state here. Between, I don't have, right? And how do I get this? Schrodinger equation. So you don't need to count it. I will tell you what it is. But you need to know that for 3D, you have this type of distribution. 2D, you have this type. Okay? So in reality, what are we talking about, right? This is example. Density of state. This is talking about the density of state. Okay, E minus EC in 3D. This is the Fermi-Dirac distribution. Okay, and this term is just, if I call this EF, FE, DOS times FE. And how about the last term? Just do an integration of DOS times FE. Then I get the N. Make sense? Any questions? Is that okay? Now, this is a toy, right? If you understand the rest is just math, you don't need to know this because we are not teaching you how to count the density of states, right? Basically, just like what we're doing here, conduction band, valence band, I draw the density of states. Do you see this one? E minus EC, right? Here telling you what is the density of states. This is DOS, right? And then you do the Fermi-Dirac distribution, you do the multiplication, you get this bump. Now, this is interesting. We never pay attention to this much. Well, it turns out that I don't have a lot of electron right at EC. Why? I have a lot of occupation due to Fermi-Dirac, but I have very low density of state. And actually, most of the electrons are away from EC. Same for the hole. For us, we don't care. We usually don't try to count the energy. We just integrate them together, then you know the N. And that is the N, right? You learn a lot of different equations in your elementary solid state physics. And at that time, I don't know if they show you this, but these are the results. For example, you get N equal to NC exponential minus EC minus F. This one is a result of this integration. Again, in this class, I don't require you to do this. Okay, it's not the purpose of this class. Okay, any questions? Okay. Now I want to talk a new topic, also very important. We're going to use it in the power device later. Incomplete ionization. So do you know we always